So welcome to Module 5 of the course. Here we're going to take all the basics that we learned about Python programming and the EarSketch API in Module 4 and start looking at how we can really look at musical algorithms to think about making music from fundamentally different perspectives. And the first perspective I want to look at that from is data sonification. And this is actually going to take all the things that we learned with set effect at the end of the last module and take it kind of to a new level, to use data from another source, in this case weather data, to drive those effects envelopes and ramps that we want to create. The field of data sonification. Very simply put, it's about using sound to express data, some non-musical data. So what that data is, it could really be anything. It could be the structure of molecules. It could be the amount of radiation that's present in a room. It could be the amount of network traffic that a server is processing. It could be the weather. It could be stock market values. It could be an image, and the pixel data in an image. It could be just about anything you imagine. The reason that sonification has become an important research field within music technology in the last couple of decades is really for two reasons. One is that it can be a very powerful creative tool, particularly in the context of algorithmic composition, to be able to take data from one domain and use it to form the structural basis of a piece of music. And so a lot of musicians and artists have been drawn to this because they want to take data that's meaningful to them in some way and use it to structure their work and use it as the foundation of their music. The other thing is that there's a lot of practical applications to data sonification. There might be some types of data, for instance, some very highly multidimensional data that can't be really expressed visually very well with a two-dimensional or even a three-dimensional representation, or maybe even a four-dimensional representation, some 3D video that's changing over time. There also might be cases where it's not practical to look at a visualization of data, but it is practical to hear it. People that have various kinds of vision impairments, they can't just look at a chart, but they might be able to hear that data. But also people that are in situations where they can't be looking at something all the time. They want to monitor something in the background while they're working. Or there might be like a fighter pilot that's trying to monitor a lot of different gauges and monitors in his cockpit all at the same time, all while he's also looking at kind of where he's going. And that can get very tricky. And so if some of those can be monitored through sound, that might be able to help in situations like that, where we can't devote our full visual attention to monitoring something. So there's a large research community that ponders these questions. I want to just look at a simple application of data sonification here, and I went to work with weather data. So what I did was I looked at some historical weather data from San Francisco, looking at the maximum temperature each day in Celsius over a 2-year period. So there's about 700 data points here. I couldn't put them all on the slide, so I just put the first 10 or 20 on the slide here. But there's about 700 or so data points here representing over 2 years the daily maximum temperatures. So you can kind of see how this changes day to day and also with the seasons and try to represent this somehow in sound. So I put this all into a Python list. I call it weather data. So you can see the beginning brackets and the ending brackets, and each of these floating point numbers is representing one daily high, and they're separated by commas. So this list in reality goes on and on for 700 items. I just put the short version here. And what I want to do is map that onto the amount of pitch shifting that I'm doing. So I want to be able to have each of these points in my envelope mapped to a successive one of these high temperatures. And so this is fairly straightforward to do, but we do need to look at a few new functions that we haven't seen before. And these are Python functions for working with lists. Max of a list will return to us the maximum value in a list. Min of a list will return the minimum value. And then len of list will tell us how many items are in the list. And so if we go ahead and look at this code here, it looks something like this. So I'm importing EarSketch like always, and then I'm declaring this weather data array, and then I init, I create a new project. I'm setting my tempo to 140 BPM. I'm finding a sound here that I want to process this way, and I'm putting it on 8 measures of music on track 1. So starting in measure 1, ending at the beginning of measure 9. Then I need to figure out, because I don't know offhand, what is across these 2 years, what was the lowest temperature in San Francisco and what was the highest temperature in San Francisco. So what I know is that I want to map this data so the absolute lowest temperature is going to be no pitch shift, so a value of 0. And the highest possible temperature across that whole time is going to go plus 12 semitones, so transpose it up a full octave. But before I can do that mapping mathematically, I need to understand what were the minimum and maximum temperatures in my list. And so that's what these 2 lines calculate, is they use these max and min functions to figure out what those max and min values were. And then I also need to figure out, I know that I placed my sound to last 8 measures here, from measure 1 to measure 9. But I don't know how many points that means that I need in my envelope. So what I do then is I look at the 8.0 measures that I need to fill, and I look at the number of items I have in my weather data list, and I just do a simple division to figure out how much space is between each of them, how close together the points in my envelope need to be. And then I do a for loop that just goes for each item in my list. So for I in range length of weather data. And so what this is doing is the first time I will equal 0, the next time it'll be 1, the next time it'll be 2, the next time it'll be 3, and so on and so forth until it's gotten to the length of that entire list, and it's gone through every item. So then I load weather data bracket I. So that gets me, first it's going to get me 13.3, then it's going to get me 9.4, then it's going to get me 9.4, then it's going to be 10, then 7.2, then 8.9, so on and so forth. So each time through the loop, temperature is going to take on the next item in my list. And then I calculate how much I need to shift the pitch by. So I know I want a number somewhere between 0 and 12. And so I'm going to get a number between 0 and 1, actually, to start. And then I'm going to multiply it by 12 to get it to that range. And so to get that number between 0 and 1, I look at my temperature minus the minimum temp. So how much are we above the minimum? And divide that by the entire range. So if my minimum were 5 and my maximum were 10, and my current temperature was 9, then we would get 9 minus 5 over 10 minus 5, which would be 4 over 5, or 0.8. So we're kind of 80% of the way up from our min to our max, is what that's telling us. And then finally, I just call set effect, and I know I want it on track 1. The effect I want is pitch shift. What I want to control in terms of parameter is pitch shift shift. The amount I want to do it is this pitch shift amount. And then where do I actually want to put this thing? Well, I know I'm starting at measure 1, so it's going to be 1 plus something. And that plus something is this step size, how far apart each of these data points is, times I. So the first time through, this is going to be at 1. Then the next time through, it's going to be at 1 plus step size. The next time it's going to be at 1 plus 2 times step size, and plus 3 times step size, and so on and so forth, until that point is getting me all the way to measure 9. So let's go ahead and look at that same script that we just discussed here inside of EarSketch. And the only reason I want to open this here is to show you that instead of 10 or 20 temperature data points in here, we have a ton of them, all 700 or so. So this list goes on and on and on and on and on with all those points with the daily temperatures that we want to sonify instead of that abbreviated list that I had in the slide. The rest of the code is identical. So I can go ahead and run this script. And then I can open up in our workstation view. Oops. Here we are in the workstation view. And you can see, just from the effect envelope as it's showing up here, you can see how it's basically plotting all of that temperature data for us. Before I play that back, I'm just going to bypass the effect for a second so you can hear the original pad sound. So there's a crescendo and a decrescendo in terms of volume that's inherent to the sound, but the pitch is not changing at all. So that's the original sound without the data from this temperature list changing its pitch. Now I'm going to turn the effect on, and you can hear how it's changing. One thing I like about this example is, first of all, it really kind of radically transforms the original sound. It kind of sounds like Flight of the Bumblebee or something. Once you're putting in all these temperature variations to control those changes in pitch. The other thing I like about it is it really does show us something through the sonification, I think. It shows us that we can hear on these kind of two structural levels. We can hear the gradual changes as we go from season to season in the data, as kind of the general register of the pitch goes up and down and rises and falls. We can also hear these very subtle variations from day to day, these tiny little kind of jumps up in tempo that last for a day or two and then come down as we have a warm front or something coming through. And I think that that's something that you can see it a little bit when you look at the data, but you really hear it in a very different way, and it brings your attention to it in a different way when you listen to it through data sonification as opposed to just seeing it with your eye. So to review what we've done in this video, we've looked at sonification as an approach to making music through algorithms, using, in this case, the set effect function from the EarSketch API to sonify weather data. What we're going to do in the next video is look at another approach to algorithmic composition, which is using randomness and chance techniques.